Imagine for a moment that everything you know about time, every tick of the clock, every passing second, isn't real. What if time as we understand it is merely an illusion, a construct of our minds, not a fundamental aspect of the universe? This isn't science fiction. It's a question that has puzzled physicists for decades. Recent studies suggest that time may not be a fundamental element of the universe, but rather an illusion emerging from quantum entanglement. Life Science 1. In fact, some theories propose that time doesn't exist in any fundamental way. Earth.com 2. If time isn't real, everything we know about reality could be turned upside down. Our understanding of cause and effect, the flow of events, and even our perception of the present moment might be fundamentally flawed. This revelation could reshape our entire worldview. In this video, we'll explore the concept that time may not exist in the way we think. We'll delve into the mysteries of quantum mechanics and how they challenge our perception of time. By the end, you'll have a new perspective on reality, one that questions the very fabric of existence. So stay with us as we journey into the heart of the quantum world, where time may be nothing more than an illusion. 1. https://www.livescience.com/physics-quantum-physics-my-p-ph-p-8-p8-p8-pi-quantum-physics-suggest? UTM_source =chat GPT. Time might be a mirage created by quantum physics study. 2. https://www.earth.com/in_UTM_chat-GPT.com. Time is an illusion and doesn't exist as we know it. Before we talk about the mysteries of the quantum field and the illusion of time, let's take a moment to understand how we experience time in our daily lives. From the moment we wake up to the sound of an alarm clock, we are governed by schedules, deadlines, and routines. Every day, our lives are measured in hours, minutes, and seconds. We watch calendars fill with appointments, birthdays, and anniversaries. The passing of time is something we feel deeply. Our bodies age, seasons change, and memories accumulate. We think of time as a river, constantly flowing forward, carrying us along its current, leaving the past behind, and taking us steadily toward the future. Before we talk about how this perception is challenged by science, consider how tightly we cling to this notion. Time defines our work, our leisure, our relationships. We structure our lives around it, often judging success or failure by how much we achieve within a certain time frame. We anxiously anticipate the weekend or the next vacation, and we reflect nostalgically on years gone by. Aging is the ultimate proof of time's relentless march. Every wrinkle, every gray hair, every milestone is a reminder that time is real, unavoidable, and constant. In our daily experience, time feels tangible, almost like a physical presence that we can measure and track. But before we talk about the contrast, it's important to realize that what we perceive as time is just one way of looking at reality. Science suggests that this linear, flowing experience may be an illusion created by our minds. In physics, particularly in the realm of quantum mechanics, time does not always behave the way we expect it to. Clocks ticking are only meaningful within the framework of our human perspective. At the microscopic level, particles do not experience time in the same sequential, predictable way that we do. What seems inevitable and ordered to us can appear chaotic, simultaneous, or even non-existent in the quantum realm. Before we talk about how this shifts our understanding, consider this: our perception of cause and effect is deeply tied to the ticking of the clock. We see events as one thing following another, a narrative neatly arranged in time. Yet, quantum physics challenges this assumption. Experiments with entangled particles show that two events can influence each other instantly, regardless of distance, suggesting that the strict sequence of past, present, and future may not be fundamental. In other words, the arrow of time that feels so real in our everyday lives may not exist at the deepest levels of reality. Before we talk about the bigger picture, notice how our minds create stories to make sense of time. Memories give us a sense of the past, anticipation shapes the future, and the present is a fleeting bridge between the two. Science, however, hints that this bridge may be a construct. The universe might not experience a past, present, or future at all. It might simply exist as a vast, timeless field of possibilities. What we feel as time could be like the surface of a calm lake reflecting ripples, while beneath it lies a still, timeless reality that defies our human perception. Before we talk about the implications, think about the contrast. Daily life tells us that time is constant, objective, and unavoidable. Physics whispers that time might be optional, emergent, and deeply mysterious. This tension between perception and reality sets the stage for exploring a universe far stranger than our clocks, calendars, and schedules would ever suggest. Before we dive deeper into the mystery of time, it's important to understand the world of quantum mechanics, the science that studies the universe at its tiniest scales. Quantum mechanics is the study of particles so small that they cannot be seen with even the most powerful microscopes. It explores the behavior of electrons, photons, and other subatomic particles, where the rules of classical physics no longer apply. In this microscopic world, reality behaves in ways that are completely counterintuitive, challenging everything we think we know about how the universe works. Before we explore the implications for time, consider one of the most mind-bending principles of quantum mechanics: superposition. Superposition is the idea that a particle can exist in multiple states at once. Unlike in our everyday world, where things are either one thing or another, in the quantum world, particles can be in many different states simultaneously until they are observed or measured. This means that a single electron can spin in two opposite directions at the same time, or a photon can travel through two different paths simultaneously. It's as if reality itself refuses to settle on one version until it's forced to choose, revealing a universe that is far less fixed and far more fluid than our ordinary experience suggests. Before we move forward, another fascinating phenomenon is entanglement. Quantum entanglement occurs when two particles become linked, even if they are separated by vast distances. When something happens to one particle, the other responds instantly, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it seems to defy the classical idea that nothing can travel faster than light. Entanglement shows us that particles are not isolated. They are connected in ways that suggest a deeper level of unity in the universe. What happens here can immediately influence what happens there, hinting at a reality where space, and perhaps even time, is not as solid or absolute as we think. Before we explore what this means for our perception of reality, it's worth noting that quantum mechanics doesn't just rewrite the rules for the very small, it challenges the foundations of logic itself. Particles can behave like waves, and waves can behave like particles. Probabilities, not certainties, govern outcomes. Observation changes reality, suggesting that the universe is far more interactive and responsive than we ever imagined. These principles aren't just theoretical, they have been proven in countless experiments, and they form the bedrock for technologies we use today, from lasers and transistors to quantum computers. Before we go further, remember that quantum mechanics opens a door to a universe that operates very differently from what we see with our eyes. Superposition and entanglement hint at a reality that is interconnected, fluid, and unpredictable. They provide the perfect stage for understanding why time, the concept we take for granted, may not exist in the way we think it does. The quantum world reveals a universe that is simultaneously strange and beautiful, a universe where the rules we rely on every day dissolve into something far more mysterious, setting the foundation for a radical shift in how we understand existence itself. Before we dive deeper into the mystery of time, it's important to understand the world of quantum mechanics, the science that studies the universe at its tiniest scales. Quantum mechanics is the study of particles so small that they cannot be seen with even the most powerful microscopes. It explores the behavior of electrons, photons, and other subatomic particles where the rules of classical physics no longer apply. In this microscopic world, reality behaves in ways that are completely counterintuitive, challenging everything we think we know about how the universe works. Before we explore the implications for time, consider one of the most mind-bending principles of quantum mechanics: superposition. Superposition is the idea that a particle can exist in multiple states at once. Unlike in our everyday world, where things are either one thing or another, in the quantum world, particles can be in many different states simultaneously until they are observed or measured. This means that a single electron can spin in two opposite directions at the same time, or a photon can travel through two different paths simultaneously. It's as if reality itself refuses to settle on one version until it's forced to choose, revealing a universe that is far less fixed and far more fluid than our ordinary experience suggests. Before we move forward, another fascinating phenomenon is entanglement. Quantum entanglement occurs when two particles become linked, even if they are separated by vast distances. When something happens to one particle, the other responds instantly, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it seems to defy the classical idea that nothing can travel faster than light. Entanglement shows us that particles are not isolated, they are connected in ways that suggest a deeper level of unity in the universe. What happens here can immediately influence what happens there, hinting at a reality where space, and perhaps even time, is not as solid or absolute as we think. Before we explore what this means for our perception of reality, it's worth noting that quantum mechanics doesn't just rewrite the rules for the very small, it challenges the foundations of logic itself. Particles can behave like waves, and waves can behave like particles. Probabilities, not certainties, govern outcomes. Observation changes reality, suggesting that the universe is far more interactive and responsive than we ever imagined. These principles aren't just theoretical, they have been proven in countless experiments, and they form the bedrock for technologies we use today, from lasers and transistors to quantum computers. Before we go further, remember that quantum mechanics opens a door to a universe that operates very differently from what we see with our eyes. Superposition and entanglement hint at a reality that is interconnected, fluid, and unpredictable. They provide the perfect stage for understanding why time, the concept we take for granted, may not exist in the way we think it does. The quantum world reveals a universe that is simultaneously strange and beautiful, a universe where the rules we rely on every day dissolve into something far more mysterious, setting the foundation for a radical shift in how we understand existence itself. Before we dive deeper into the mysteries of time, it's essential to understand the concept of the quantum field, the very fabric of reality itself. Unlike the way we normally think about the universe, where matter is made up of separate solid particles, the quantum field suggests that everything we see, touch, and experience emerges from invisible fields that permeate all of space. These fields are everywhere, all the time, forming the underlying structure of the cosmos. They are not just a backdrop for the universe, they are the universe itself, the fundamental layer beneath all matter and energy. Before we go further, imagine the universe as an ocean. On the surface we see waves, distinct, separate forms that seem individual, but in reality, those waves are nothing more than ripples moving through a continuous unified body of water. Similarly, what we perceive as particles, electrons, photons, quarks, are not tiny, isolated objects. They are excitations, ripples, or disturbances. In the quantum fields, each particle is like a momentary wave appearing in an invisible sea that stretches across the universe. When we see a particle, we are really observing a localized vibration of a field, a temporary manifestation of something much deeper and more fundamental. Before we explore the implications of this idea, consider how revolutionary. Traditional physics treated particles as the building blocks of reality, independent entities moving through empty space. Quantum field theory flips this notion completely. Particles don't exist on their own, they are expressions of the field. The electron isn't an isolated dot, it is the electron field, vibrating in a specific way, at a specific location. Photons are excitations of the electromagnetic field, and every other particle emerges from its corresponding field. In this view, the universe is not made up of things, it is made up of fields, in constant motion, interacting, creating, and transforming. Before we go further, notice how this perspective changes everything. If particles are just excitations of a field, the distinction between here and there becomes blurry. Matter is not a collection of separate independent objects, but a network of interconnected fields. This interconnectedness is at the heart of why quantum mechanics seems so strange, and why concepts like entanglement make sense. Two particles influencing each other instantly across space is less mysterious if they are just expressions of the same underlying field. The universe becomes less like a collection of billiard balls and more like a single vast vibrating system where every part is fundamentally connected. Before we explore the consequences for time, think about the elegance of this idea. Fields are eternal, continuous, and omnipresent. Particles appear and disappear, but the field remains. This suggests that the building blocks of reality are not fixed or permanent. They are dynamic, emergent, and deeply. What we perceive as matter, energy, or even the passage of time may simply be patterns arising from the deeper timeless quantum field. Understanding this helps us prepare for the next revelation in a universe defined by fields, rather than discrete particles. Time may not exist the way we think it does. Reality, at its most fundamental level, may be far more fluid, interconnected, and mysterious than our senses allow us to perceive. Before we explore the deeper mysteries of the universe, it's important to understand how our ideas of time have evolved. For centuries, we lived with the Newtonian view, a perspective that shaped science, philosophy, and everyday life. According to Newton, time is absolute. It flows uniformly, like a steady river, independent of anything else in the universe. Clocks tick, planets orbit, and events unfold in a predictable linear sequence. Time, in this framework, is fixed and universal. 1 second here is the same as 1 second anywhere else in the cosmos. Past, present, and future are neatly ordered, and the universe marches forward according to a precise mechanical clockwork. This idea made sense for centuries. It was logical, measurable, and easy to grasp. It gave humans a sense of certainty and control, a framework for understanding cause and effect. Before we explore how this changes, consider the quantum perspective, which challenges the very foundation of Newtonian time. In quantum mechanics, the idea of a universal, absolute clock breaks down. At the subatomic level, particles do not follow the rigid flow we are used to. Electrons, photons, and other fundamental entities do not experience time as a continuous progression. Instead, they exist in probabilities and potentials, where sequences of events are not strictly ordered. The universe, at its smallest scales, behaves in ways that are disconnected from the tidy flowing time of classical physics. Time becomes less of a fixed backdrop and more of an emergent property, dependent on relationships between events, rather than an independent entity. Before we go further, think about the implications. If time is not fundamental, the concept of now is relative, and the past and future may not be as rigidly defined as we believe. In the Newtonian view, one event inevitably follows another. In the quantum realm, events can exist in superposition, multiple possibilities coexisting until measurement or observation occurs. Cause and effect are not always linear. What appears to us as the flow of time may simply be our perception trying to make sense of a deeper timeless reality. In this way, the universe at the quantum level is far less predictable, far less constrained by the clock, and far more mysterious. Before we move ahead, it's important to note that this doesn't mean time doesn't exist at all. It simply means it may not exist in the way we have always imagined. Quantum mechanics suggests that time is not a universal ruler that measures everything uniformly. Instead, it may emerge from the interactions of fields and particles, a kind of shadow of more fundamental processes happening beneath the surface of reality. The steady river of Newtonian time is replaced by a dynamic, probabilistic landscape, where sequences are fluid, and the very notion of a present may be meaningless. Before we explore the consequences for our understanding of reality, consider this striking contrast in classical physics. Time is solid, unchanging and ever-present. In quantum mechanics, time is flexible, relational, and emergent. The clock we watch every day is no longer the absolute arbiter of events. It's a human-made tool to measure what is fundamentally fluid and uncertain. Understanding this contrast is key to grasping why the quantum field challenges everything we think we know about the universe, and prepares us to rethink one of the most basic assumptions of our lives, that time is real. Before we dive deeper into the mysteries of time, it's important to understand a puzzle that has haunted physicists for decades: the problem of time in quantum gravity. In classical physics, time is simple and straightforward. It ticks along steadily, providing a backdrop for all events in the universe. But when scientists try to combine quantum mechanics with general relativity, the theory that describes gravity, and the large-scale structure of the cosmos, this neat picture begins to fall apart. Quantum gravity, the theoretical framework that seeks to reveals a universe where time does not emerge naturally. At the most fundamental level, the equations that describe quantum gravity don't include a separate flowing time. Instead, the universe appears timeless, a static structure where past, present, and future are not clearly defined. Before we explore why this matters, imagine the consequences. If time doesn't exist as a fundamental element, then everything we assume about the unfolding of events is called into question. In quantum gravity, the universe is described as a set of relationships between fields and particles, rather than a sequence of moments passing along a temporal line. Change and movement still occur, but they do so without an underlying clock guiding them. This challenges the way we think about causality. The familiar idea that one event causes another, that effects follow causes in a neat chain, may not hold at the deepest levels of reality. Instead, the universe may operate according to rules that are entirely. Before we go further, it's important to grasp how radical this idea is. Our brains are wired to experience time as continuous and linear. We remember the past, live in the present, and anticipate the future. But in the quantum gravitational view, this familiar flow could be an emergent phenomenon, something that arises from complex interactions of fundamental fields, rather than a basic ingredient of the universe. What we perceive as time could simply be a convenient illusion, a way for conscious beings to organize experiences in a coherent narrative. At the most fundamental level, the universe may exist as a timeless landscape, where all events are laid out in a vast interconnected structure, with no intrinsic past or future. Before we examine the implications, consider how this challenges our understanding of the universe's structure. If time is not fundamental, space
Self may also be more fluid and relational than with the geometry of the cosmos. The behavior of black holes and even the Big Bang are described differently when time is removed from the equations. Concepts like beginning, end and duration lose their absolute meaning. The universe becomes a network of possibilities, a web of relationships and interactions that exists independently of the ticking of a cosmic clock. Before we move forward, reflect on how this changes everything we thought would. The problem of time in quantum gravity suggests that the universe is far stranger than our senses can perceive. It hints at a reality where the flow of seconds, minutes and hours is not fundamental but emergent, shaped by interactions and relationships rather than by a universal clock. Understanding this problem is essential for anyone seeking to grasp the true nature of the cosmos and our place within it, because it forces us to question the very framework through which we experience existence. Before we explore the depths of the quantum world, it's important to consider one of the most thought-provoking ideas about time, Carlo Rovelli's relational theory. According to this perspective, time is not a fundamental element of the universe, ticking along independently like a cosmic clock. Instead, time is a measure of relationships between events. In other words, time is not something that exists on its own. It emerges from the way events interact and influence one another. Without these relationships, there would be no past, no present, no future, just a timeless network of occurrences waiting to be connected. Before we go further, imagine looking at the universe, not as a stage on which events unfold, but as a web of interactions. One particle affects another, one field influences a second, and the pattern of these interactions gives rise to what we perceive as time. If nothing interacts, there is no clock ticking, no progression from one moment to the next. Time, in Rovelli's view, is not a pre-existing backdrop, but an emergent property that arises when events relate to one another. It is in essence a measurement of change rather than an absolute entity. This subtle shift in perspective turns our traditional understanding of reality upside down. Before we explore how this connects to quantum mechanics, consider how revolutionary classical physics treated time as universal and linear, a constant flow experienced the same everywhere. Relational theory challenges this by suggesting that different observers might experience time differently, depending on the relationships between the events they observe. In this sense, time becomes deeply contextual. There is no single absolute clock governing the universe. Instead, the when of an event is meaningful only relative to other events. This perspective dissolves the idea of an objective past and future, and replaces it with a dynamic interdependent structure of moments. Before we connect this to quantum mechanics, it's important to note that relational time aligns beautifully with the principles of the quantum world. In quantum mechanics, particles exist in superpositions, probabilities, and entangled states. Their behavior does not depend on a universal temporal flow but on interactions and measurements. Rovelli's relational theory mirrors this reality. Time is not imposed externally, it arises internally from the relationships and correlations among quantum events. When one particle interacts with another, it defines a sort of clock relative to that specific interaction. This is entirely consistent with the strange, non-linear and probabilistic nature of quantum mechanics, where order and sequence emerge from entanglement and measurement rather than a pre-existing temporal framework. Before we continue, consider the philosophical implications. If time is deeply linked to consciousness, then our experience is fundamentally personal and relate. Two observers in identical circumstances may perceive time differently. Not because the universe itself has changed, but because consciousness interprets events uniquely. This perspective bridges the gap between the seemingly objective flow of time in classical physics and the fluid probabilistic nature of time in quantum mechanics. Consciousness becomes the lens through which the timeless quantum world is translated into the flowing sequential reality we experience. Before we think about how this idea reshapes our understanding of life and existence, If the passage of time is not absolute but is filtered through consciousness, then much of what we consider urgent, fleeting or irreversible may be a matter of perception rather than our memories, our sense of aging, and even our anticipation of the future are not necessarily dictated by the universe, they are constructed by the mind. This suggests a profound interconnection between the observer and the observer, where consciousness not only perceives reality but actively shapes the temporal structure we take for granted. Before we move on, remember that exploring consciousness in relation to time is more than just a philosophical exercise. It opens a window into understanding why time feels the way it does, why it can stretch and contract, and how our minds translate the timeless fabric of the quantum universe into a lived experience. In this view, time may exist not as a universal ruler, but as a dance between awareness and the underlying eternal structure of reality. As we've explored in this video, the concept of time may be far stranger than we ever imagined. From our everyday perception of clocks, schedules, and to the mind-bending insights of quantum mechanics, time may not be a fundamental part of the universe at all. Particles exist as excitations in quantum field. The flow of events is not absolute, and relational theories suggest that time emerges from relationships rather than ticking clocks. Even consciousness itself may play a crucial role in shaping how we experience the passage of time. What feels real, constant, and inevitable could in fact be inelegant illusion crafted by the interactions of events and awareness. The universe, when seen through this lens, is a far more mysterious and interconnected place than our daily experience suggests. Embracing this mystery doesn't just challenge our understanding of physics, it invites us to reconsider the nature of reality, our perception, and our place in the cosmos. By exploring these profound questions, we open ourselves to a deeper awareness of existence, one that transcends the limitations of linear time and encourages curiosity, wonder, and reflection. If this journey into the nature of time and reality sparked your curiosity, don't stop here. Keep questioning, keep exploring, and let your mind expand into the infinite possibilities of the universe. And if you enjoyed this video, make sure to like it and subscribe to our channel, so you never miss a new exploration into the mysteries that shape our